This is section 6.5, trapezoids and kites. So our definition of a trapezoid is that it has exactly one pair of opposite sides parallel. So there's only one set of parallels in every trapezoid. Those parallels are known as the base sides. So they're the bases. So every trapezoid has two bases, and those bases are the parallels. Our non-parallel sides are known as the legs. So our parallels are the bases, the non-parallels are the legs. We also get what are known as base angles. Just like in a isosceles trapezoid, the base angles are the angles on each side of a base. So there's two pair of base angles. So we have a pair of base angles at each end of base 1. And we have a pair of base angles at each end of base 2. Now, keep in mind that because we have parallel lines and our leg creates a transversal, that our leg creates a set of consecutive interior angles for parallel lines. So we do get to use that consecutive interior angles theorem for parallels with our angles at each end of the same leg. So now that we know a trapezoid has one pair of parallels, we get an isosceles trapezoid. So isosceles trapezoids, like isosceles triangles, have congruent legs. So when you have congruent legs on a trapezoid, it is isosceles. If it is isosceles, then it will have congruent legs. Also, similar to triangles, we can put in a mid-segment of a trapezoid. So just like in our triangle, it connects midpoints, but this one is a little more specific. It has to connect the midpoints of the legs. So it doesn't connect the midpoints of the bases, it connects the midpoints of the legs. So you find the midpoint of the first leg, the midpoint of the second leg, and your mid-segment connects them. Theorem 614 and 615 are converses of each other. So if you put them together, they will create an if and only if statement. So we're going to have a trapezoid. So we're going to have the pair of parallels. And if we have a trapezoid that is isosceles, so it has the congruent legs, then the base angles are congruent. So my two angles with base 1 are congruent. My two angles with base 2 are congruent. And conversely, if I have a trapezoid with congruent base angles, then it's going to have to be isosceles. Theorem 616 is if for a trapezoid to be isosceles, it has to have congruent diagonals. So if you have a trapezoid with congruent diagonals, it's isosceles. And if you have an isosceles trapezoid, the diagonals are congruent. Our mid-segment theorem for a trapezoid is very similar to the mid-segment theorem for a triangle. The mid-segment will be parallel to both of the bases, and our mid-segment length is going to be half the sum of the length of the bases. So our mid-segment length is equal to half the sum of the length of the bases. Our definition of a kite is a quadrilateral that has two pair of consecutive or connected sides. So you're going to have two short sides connected here at K to get that segment KI is congruent to segment KE. We have two longer segments that have a common endpoint at T. So segment IT will be congruent to segment ET. So you're going to have two sets of consecutive or connected congruent sides. In a kite, the diagonals are going to be perpendicular, and we can actually use this to prove that we have hypotenuse leg congruence between the two triangles on each side of the diagonal to get that we actually end up bisecting one of our diagonals. So it's usually the shorter diagonal that gets bisected, but our diagonal that goes from the vertice where the non-congruent sides are connected. Also, For a kite, it will have exactly one pair of opposite angles congruent, and that happens to be the angle formed by the non-congruent sides. So where my short side and my long side meet creates an angle, and it's congruent to the one opposite. So when you fill in your chart, remember that the parallelogram had the three special parallelograms, and we filled all of that information in. When you look at the chart, you will notice that trapezoid does not get its own column. The trapezoid, we just have the definition. The rest of our information went with isosceles. So a trapezoid has exactly one pair of opposite sides parallel, and the isosceles trapezoid has exactly one pair of opposite sides congruent. Also, down here where it says consecutive angles are supplementary, in any trapezoid, because of my parallel lines, my leg creates a transversal. So we create consecutive interior angles with the leg. So you're going to work with one leg's angle pair. They're going to be your consecutive angles that are supplementary. You also have your definition of the kite and its theorems as well. So make sure that you're filling in your information for this chart. It's going to be quite useful over the next several lessons. So our first set of examples deals with our vocabulary for trapezoids. The bases are the parallels. So I find the arrows for the parallels. So that means that I'm working with segment QR and segment PS. So that's answer choice A. My non-parallels, which are PQ and RS, are the legs. So that's answer choice B. The diagonals join non-consecutive vertices, so Q to S and P to R. So my diagonals are answer choice C, number 3. With the angles, my base angles are on the same base. So Q and R are with the same base, and then angle P with angle S are with the same base. So angle P and angle S are base angles, and that means that our opposite angles, which happen to be connected by a diagonal, are Q and S. Using properties of our quadrilaterals to answer always, sometimes, and never. So a trapezoid, by definition, has exactly one pair of opposite sides parallel, and a parallelogram, by definition, has both pairs, and those two things can never happen together. So you can never have one pair and both pair parallel in the same shape. The next one wants to know about the bases of a trapezoid being parallel. This is actually our definition of base. So this is always going to be true. The next one wants us to look at the base angles of an isosceles, and that's important, trapezoid being congruent. In an isosceles trapezoid, we have our theorem 614 that says when it's isosceles, they're congruent. And we have theorem 615 that says when they're congruent, it's isosceles. So this is always going to happen. The next one wants to know about the legs of a trapezoid being congruent. This happens in an isosceles trapezoid, not every trapezoid. So this is our definition of isosceles, to have the legs congruent. So this is sometimes. So only when our trapezoid is isosceles are the legs congruent. So when we look at this set of diagrams, we see that there is only one set of parallels. So these are trapezoids. And in the first one, there happens to be a set of congruent legs. So this is isosceles trapezoid. We're going to look at the angles section. For the isosceles trapezoid, we get to use, so for the isosceles trapezoid, we get to use this theorem, that our two pair of base angles are congruent, and this is only true for the isosceles. So this means angle A will be congruent to angle B, and angle D will be congruent to angle C. So angle B is also going to be 53 degrees. For all of the remaining items, we're going to use the fact that we have consecutive interior angles that are supplementary. So we have a common transversal between our parallels. So my measure of angle A, which is 53 degrees, plus the measure of angle D is going to have to be 180 because consecutive interior angles of parallel lines are supplementary, and we have that with trapezoids. So when we subtract the 53, the measure of angle D is 127 degrees, and because this is an isosceles trapezoid, the measure of angle C will be the same as that as well. In problem 11, we do not have any congruent legs. So in this one, we only get to use the fact that because of the parallels, our consecutive interior angles are supplementary. So that means we're working with angle A and D, and we're going to work with angle B and C. So the 91 for angle A plus the measure of angle D is going to be 180, and the 132 plus the measure of angle C is going to be 180. So our measure of angle D ends up being 89, and our measure of angle C ends up being 48 degrees. In the next set of problems, we're going to be working with the lengths of the mid-segments. So we're going to use our mid-segment theorem, and we're dealing with the lengths. So the mid-segment is half the sum of the length of the bases. The bases are the parallels. Our mid-segment is in the middle. So this is just a matter of substituting in the values and then solving the equation. So in the first example, my mid-segment is x. It is going to equal half the sum of the bases, which are 7 and 13. So this is going to be x equals half of 20. So this x is equal to 10. In problem 14, my mid-segment is the unknown. It is equal to half the sum of the bases, which are 22 and 18. So order of operations, we do the addition problem first, and then we take half. So this mid-segment is equal to 20. We can use our mid-segment to calculate a base length as well. So we can, if we have a known mid-segment, it is still equal to half the sum of the bases. It's just that this time one of our bases is a number and one of our bases is a variable. So we're going to have to use our algebra skills. So we distribute to get half of 8 is 4 plus half of x. We're going to subtract to get 7 equals half of x, and when you divide by a half or multiply by 2, we get 14 for the value of x. So we're just substituting into the formula. The mid-segment, the one in the middle, is equal to half the sum of the bases, the parallels. So one of them is 24, the other one is x. We distribute, so 13 equals 12 plus half of x. We subtract, so 1 equals half of x. And then we get rid of the 1/2 to get 2 is equal to x. In a kite, finding the measures of the angles, we're going to use two facts. Exactly one pair of opposite angles are congruent, and the sum of our interior angles is 360. So remember, in a kite, you have your two sets of consecutive angles, your consecutive congruent sides. Our congruent angles are the angles opposite each other with the intersection of our congruent sides. So in this problem, we're going to get that angle E is congruent to angle I. So my measure of angle I is also going to be 124 degrees. To find the fourth angle, we use the fact that the sum of our angles is 360. So we're going to add together all four of our angles and set it equal to 360 degrees. So we have our measure of angle K. We have the 124 for angle E. We have the 124 for angle I. And we have the 32 for the measure of angle T. So my measure of angle K is going to be added to. So we calculate to get 280. And when we subtract, the measure of angle K ends up being 80 degrees. So our congruent angles are the angles at the intersection of the non-congruent sides. So our congruent angles are at the intersection of the non-congruent sides. If you happen to be missing both of them, simply use the same variable. But since I know one, the other one is the same. So my measure of angle E is going to be 118 degrees. And then I use the fact that my sum of the four angles is going to equal 360 degrees. So my measure of angle K plus the 118 for I plus the 74 for T plus the 118 for E. So this is the measure of angle K plus 310 degrees. And when we subtract, the measure of angle K is 50. Our last example problem is finding the length of a side. And this is actually going to use several facts. So we know that we have two pair of consecutive sides congruent. So we have our two short sides congruent, and we have our two longer sides congruent. And then we're going to use the fact that because all of our measurements are on the diagonals, that the diagonals are perpendicular to each other. This happens to create two pair of congruent right triangles. So I have two pair of congruent right triangles. So I'm going to let x be the length of the shorter side and y be the length of the longer side. And this actually requires that we end up using the Pythagorean theorem. My leg pieces come from the diagonal, and my hypotenuse is the side of the kite. So for my first small congruent triangle, I'm going to do 4 squared plus 2 squared equals my x squared. So that's 16 plus 4 to get 20. And to remove the square, we take the square root. And since we're dealing with measurement, we only need the positive square root, and the square root of 20 rounded to the nearest tenth is 4.5. So this is the length of the two shorter sides. And then because my diagonals are perpendicular, I've created a right triangle. So this means that I can take the leg of 2 plus the leg of 6 squared and get the hypotenuse, which is the side of my kite squared. So this is 4 plus 36 to get 40. And when we take the square root of 40 to get the value of y, we get 6.3. So if you have to find the side length and you only have the diagonals, we use the fact that opposite sides are congruent, so we really only have two calculations. Because the diagonals are perpendicular, we create right triangles. Because we have right triangles, we can use the Pythagorean theorem in order to calculate the missing side length.